On Wednesday, we defined two terms, a vector and a scalar. Who can tell me the difference between the vector and the scalar? Don't remember? Hey, if you don't remember, think of the vector serial, right? Versus scalar serial, of course, one of them has, go ahead. Good. And a scalar has only magnitude. Good. So a vector has both magnitude and direction, as opposed to a scalar, which has only the magnitude. Give me an example of a vector. Give me an example of a vector or a scalar. I don't care which one. You just tell me which one you're giving me, a vector or a scalar, okay? Yeah. Good. Speed is a scalar. Direction doesn't matter. My average speed when I go to Edmonton and back might be 105 kilometers per hour. Good. Give an example of another vector or scalar. Just tell me which it is. Yep. Good. Position is a vector. If we want to know where something is, we need to know exactly what direction it is relative to something else as well. Good. Another one? What about distance? Vector or scalar? How far something's traveled? Oh, come on. We're 3 days into class here now, you guys. Distance, a vector or a scalar? Fraser? Good. It's a scalar. And of course, the units for distance are meters. What about velocity? A vector or a scalar? This one's easy to remember, right? Speed is a scalar. Velocity is a good. Thank you, Bo. Velocity is a vector, and of course, the typical units for that are going to be meters per second. What about displacement? Can you define displacement for me, by the way, before we say whether it's a vector or a scalar? Can you tell me what it means? Yep. Good. It's the change in position. So if the symbol for position is d, then the symbol for displacement, the change in position, would be delta d. Position, I forget who it was. Somebody told me that position was a vector. Displacement would be a go ahead. Yeah, displacement is going to be a vector as well. Good. We learned a couple equations over the last couple of days. V equals d over t and V equals d over t with a slight modification. One of them is for speed, one of them is for velocity. Which one's which? Equation 1, equation 2. Which one's for speed? Both? Good. And obviously the other one is for average velocity. Good. What does this delta d stand for right here in this speed equation? Yeah, distance. The distance traveled, which is, you know, you could say that as a change. Sure, it's got a delta in front of it. And delta t, of course, stands for a time interval, how much time has gone by. Not what time it is. Okay, it's not, you know, what's your speed at 9:51 in the morning. Delta t stands for how much time has gone by as you've driven or as you've walked or as you've traveled a certain distance. What does this delta d stand for? I'll give you a hint. It's not distance. Somebody said it? Good. It's displacement. Good. Now, there's a couple ways that we can use to find displacement depending upon the situation. Displacement can be df minus di, and displacement can be delta d1 plus delta d2. What's the difference here? What's df stand for? What is d? Forget about the f for a second. What's d? It's not distance, right? Because that's delta d. It's not displacement, because that's delta d with the arrow over it. What's d? Good, it's position. So df would be, right, final position, and di would be initial position. So in other words, if you're given two different positions, where you are versus where you were, we're going to subtract them. Delta d stands for displacement. So the total displacement can be the displacement in one stage added to the displacement in another stage. Let's keep that straight. Okay, a lot of times we make a mistake and subtract displacements to get a total displacement, or add positions to get a total displacement. We can't do that. Okay, if we've got two different positions, in other words, two different places where an object is, then we're going to subtract them to get displacement. But if we've got two different displacements, how far an object has traveled, two different intervals of displacements, then we're going to add them together to get the total displacement. Let me give you a quick little example, and I want you to tell me whether we're going to use the first version or the second version in order to get displacement here, okay? So let's say that a car is driving north to Edmonton. Red Deer is 150 kilometers north of Calgary. Edmonton is 320 kilometers north of Calgary. How are we going to find the displacement from Red Deer to Edmonton? Version 1 or version 2? Red Deer is 150 kilometers north of Calgary. Edmonton is 320 kilometers north of Calgary. Are those positions or displacements? Are those where Edmonton is, or how far something's gone? It would be number 1, right? The position of your car as you're driving to Edmonton initially is 150 kilometers north of Calgary. The final position is 320 kilometers north of Calgary, so we're going to subtract those in order to get the total displacement. Good. One more. We drive 150 kilometers to Red Deer. Then we drive 170 kilometers to Edmonton. What's the total displacement between us and Edmonton? Version 1 or version 2? Are those positions or are those displacements? We drove 150 kilometers, then we drove 170 kilometers. Are those where we are or how far we've gone? Right, how far we've gone. So those are displacements. So we're going to add those together, right? We subtract positions to get displacements. We add displacements to get displacement. Good? All right, we did a couple examples yesterday of speed, distance, time problems. We're going to do one more example here right now. 1.7 on page 37 of your textbook here. Again, just like I've said before, you don't need to write down a question that appears in your textbook. I would like you to reference it and just say, in your notes, 1.7, page 37, just so you can go back to it when we know, when you see your solution, you know which question it goes with. It says, find the average velocity of a student who jogs 750 meters to the east in 5 minutes, does static stretches for 10 minutes, and then runs another 3 kilometers to the east in 30 minutes. What's the average velocity? Well, we've got some times here. What's the total time here? My time interval over which this event has occurred. Is it 5? Is it 10? Is it 30? Or is it, sorry? Not 25, no. This is 5, 10, and 30. $45, yeah, it's going to be 45 minutes, good. Now, we said usually we go in seconds. It's okay to go in minutes. Okay, we'll leave it there for now. We'll see if it's convenient to leave it there in the end or whether we should convert it in the end. We'll deal with that when we get a little bit further through this question. All right. What about these 750 and this 3 kilometers thing here? Are those positions or are those displacements? Are those where the student is or how far the student's gone? How far the student's gone. Those are displacements. So we're not going to call those DI and DF. We're going to call those delta D1 and delta D2. Delta D1 is 750 meters. Delta D2 is 3.0 kilometers. We'll define east as positive, and then we don't have to write in the letter every time. All right. We got a bit of an issue here now. I said that usually we use meters and we use seconds, but we can use other units sometimes, and we can here as well if we want. But we do have to be consistent. So if we've got one displacement as meters, the other one has to be meters. Or if we've got one displacement as kilometers, the other one has to be kilometers. Let's go with meters here. D1 is 750 meters. D2 is 3,000 meters. 3 kilometers is 3,000 meters. We multiply it by 1,000, right? You guys remember that? There's 1,000 meters in a kilometer. We want to find the average velocity, so let's use that velocity equation, delta d over delta t. Do we add those displacements or do we subtract them? Add or subtract? If we have two different positions, we subtract. If we have two different displacements, we add them. So let's add these together. Becomes 3,750 meters over, do you want to leave it as 45 minutes? We could, but if we do, that's going to give us an odd set of units for velocity. What are my units going to be for velocity if I leave that? It's not going to be kilometers per hour or meters per second. It would be, Fraser? Meters per minute, which is okay, but it's just kind of odd. It's not usual, right? Let's convert this to seconds. Okay, if you left it in minutes, that would be okay. I wouldn't mark it wrong, as long as you expressed your answer in the correct units of meters per minute. Okay, it probably makes more sense, though, to convert this to seconds. What is 45 minutes in seconds? 45 times 60 is 2,400, 2,700. That's going to make a little bit more sense for us. Now that we've got 2,700 seconds on the bottom, our final answer will be in meters per second. What is the answer there? We get 1.38889 meters per second. Where should we round that to? How many digits? Yep. Question? Good. Yeah, it is 2 digits, yes. I almost made the same mistake as you. I was going to say 3 as well. But it is 2, you're right. Because it's 3 digits here, 3 digits here, 3 digits here. But these guys are only 2 digits. So the final answer should be 2 digits. What should it be? 1.4. Yeah, 1.4 meters per second. Once again, as I mentioned yesterday or the day before, if you're not quite sure about this whole significant digit thing right now, don't panic about that. We're going to have a quiz on on Tuesday. But if you make a mistake on significant figures on Tuesday's quiz, I'm not going to mark you wrong on that, okay? We'll deal with that later on. I want you to get lots of practice on that before I start marking you wrong on that. Okay, but I do want you to be aware of it at least. Is that good? Now, this is a vector, and we got a positive value, so what does that really mean? 1.4 meters per second to the, yeah, we defined east as positive, so our final answer is really 1.4 to the east. We don't really need to write in east because we already defined east as positive, and we got a positive value. If you want to write in east, go ahead, but you don't have to. All right, I'm going to give you a couple minutes to work on a couple of problems here. See what you can do with those. We'll take a look at them, and then we'll show you a little video with a very, very short worksheet that goes with it. All right, let's take a look at question number 2. It says, person A runs the 100-meter dash in 9.84 seconds, then tags person B, who runs 200 meters in 19.32 seconds. Then B tags out of shape person 3, who runs 400 meters in 1.9 minutes. Find the average velocity for the trio. Compare it to each individual's average velocity and assume they're all running in a straight line. All right, so let's say are these displacements or positions, these 100 meters, these 200 meters, these 400 meters? Are they how far somebody's traveled, or are they where somebody is? Displacement or position? Yep. Good, they're displacements. They're how far somebody's traveled. We're going to call it dA. We were calling it D1, delta D1, delta D2, delta D3. We're going to call it delta dA here because we're just going to be consistent with the question. Person A runs 100 meters. We're going to say that person B runs 200 meters, and person C runs a total displacement of 400 meters. Now, we don't need to worry about defining what's east and what's positive and what's negative, because in the end, they're all in the same direction. Whatever direction that is, whether it's east or west or north or south, we'll call that positive. So they're all positive displacements. Now, we're going to say the time interval for person A is 9.84 seconds. That's fast. Okay? That's a world record from the 1980s. Okay? Now it's not a world record. I think the world record now is 9.59 seconds. But that's still fast. That is, believe it or not, at peak speed. When that guy is running 9.84 meter, at peak speed, that's almost at 50 kilometers per hour. So if you're late for school and you're running down the road at this speed to get to school, you could get a ticket for speeding in a school zone because you're running too fast. Something like 45 to 50 kilometers per hour. That'd be impressive to watch a guy running 50 kilometers per hour. Right? I could do it. I could do it. Maybe not quite. Person B is running the 219.32 seconds. That's also very fast. 19.32 seconds. I wish I could run anywhere close to that fast. Person C, I could beat this person. I think I could beat this person. 1.9 minutes is the time that it takes person C to run 400 meters. In fact, I know I could beat this person. Now, we've got all our times in seconds except for one. Let's make our other one in seconds. We want to be consistent, right? We could go minutes if we wanted for all of them, but we might as well go seconds. 1.90 minutes is how many seconds? 114 seconds, is that exactly? Okay, 114 seconds. How'd you get that? Good. 1.9 times 60 is 114. All right, we want to find, first of all, the velocity, the average velocity of everybody. So let's say average velocity for everybody is displacement over time. The total displacement here is what? We add these or subtract them? Funny enough, it seems a little bit easier when you have three of them, because when we have three of them, most people don't look at it and say, oh, I think I subtract them. Like, which ones do I subtract, right? When we have three of them, almost certainly we're going to add them. These are displacements. We add displacements. We get 800 meters. What's my total time? We got to add those as well, right? What do we end up getting there for the total time? Yep. 143.16 seconds. Thank you. And when we do that, I assume we get 4.89 meters per second. So not overly fast. That's a quick run. That's a quick jog. That's a quick jog. 4.89 meters per second. All right. Now it says to calculate the average velocity of each individual and then compare it to the average velocity of the group here. We're not going to go through all three of these because they all work exactly the same. We'll do the first one. And if we're OK with that, then we should be OK with the other two as well. So let's say the average velocity of person A is displacement of person A divided by the time of person A. That's going to be 100 meters divided by 9.84 seconds. We do that math, and it works out to be 10.2 meters per second. Now, that's average. That means the average velocity of this person was somewhere in the range of 36 kilometers per hour. If you ever watch a 100-meter run, you know that for the first 50 to 60 meters, the person is accelerating. What's the speed that they start at? 0, right? So for the first half of the race, they're going slow. They speed up, and at about the 60-meter point, they reach the peak speed, which is much, much greater than 10 meters per second. It's somewhere in the range of 15 meters per second, which again is somewhere in the range of 50 kilometers per hour. Now, we use the same method to find the average velocity for person B. We find that it's 10.4 meters per second. It's actually faster. Why do you think someone can run a 200-meter run at a bit of a higher pace than a 100-meter run? Even though it's further, their average velocity can be greater, usually is greater for 200 meters than for 100 meters. Any idea why? Yes. They only have to accelerate once, right? They only have to accelerate for the first 50, 60 meters, and then they're already moving fast. So the second half of the race, they might start getting a little bit tired, but they don't have to speed up. They've already done that. So they can maintain it. and they should have a slightly higher base. And the third one, of course, 3.51, which is not very good. Compared to the other ones, not very good. Is that okay? We're okay? The people that asked me to do that, it's okay? All right. Let me just take a look at the clock here. Okay, I think we can do this here.